Another very classical exercise here. Map fixed points, question mark, stability, question mark. Pause the video and start calculating. Right, for our fixed points, we need to have the situation that f of xy should be equal to xy. So that just boils down to two equations. So f of xy, that's going to be x squared minus 5x plus y. And then that should be equal to x. And then x squared should be equal to y. So here we just say component-wise, f of xy is equal to xy. Solving this is not so hard because we can just substitute y equal to x squared in that first equation here. So we have x squared minus 5x plus x squared equal to x. Or that gives us 2x squared equal to 6x, dividing by 2 here. And then we can immediately see that the solutions here for x are x equal to 0 and x equal to 3. Figuring out what y is trivial because we then just need to square that. So in this case, y is also equal to 0, and here y is equal to 9. So this gives us our two fixed points, the origin and the point 3, 9. If you want, you can pause the video again to continue the calculation to try and figure out the stability of these fixed points. First step is obviously calculating the Jacobian. Now for the Jacobian, we will have a matrix, and the first line of that matrix will consist of the first equation. So the first equation, that's actually going to be this guy here. So this first equation, but taking the partial derivatives with respect to x for the top left element and with respect to y for the top right element of our matrix. So if we have x squared minus 5x plus y, and we take the derivative with respect to x, it's going to bring us 2x minus 5. And then for the derivative with respect to y, we just get 1. Second line of our matrix is we take x squared and then construct all of the partial derivatives. So first up, that's going to be 2x. And since there's no y in x squared, this element over here is 0. So this is our Jacobian. And if you want, you can pause again now to really take the final steps to make statements about the stability of these fixed points. Okay, let's look at the origin in terms of stability. So first of all, we need to fill out the origin in our Jacobian matrix. So in that case, the matrix becomes minus 5, 1, 0, 0. And the question is, what are the eigenvalues of this matrix? Now, if you have a triangular matrix like this, where you have a 0 over here below the diagonal, that means that the eigenvalues are just the diagonal elements. If you're not convinced, then you just quickly write down again the determinant that you need to solve, like so. But then you quickly figure out, indeed, if you put this equal to 0, that there's two solutions, which are 0 and minus 5. One of them, 0 namely, in magnitude is smaller than 1. The other, minus 5, in magnitude is bigger than 1. So this tells us that in this particular case, we're dealing with a saddle point. Good. Next step is finding the results for 3, 9. So for 3, 9, our Jacobian matrix now becomes, so 2 times 3 is 6 minus 5, that's 1. And then we have 1, 2 times 3, 6, and then 0. Now in that particular case, the determinant is 1 minus lambda, 1, 6 minus lambda. And if we put this equal to 0, then we get minus lambda plus lambda squared minus 6 equal to 0. Just alphabetizing this a little bit gives us so lambda squared minus lambda minus 6 equal to 0. Now we have a quadratic equation, so let's just figure out the solutions. The solutions are minus the term of lambda here, minus the coefficient of lambda, so that's 1, plus or minus the square of that thing, minus 4 times the product of this guy and that guy. So that's going to give us plus 24, and then dividing the whole thing by twice the coefficient of lambda squared. 25, of course, gives us 5 squared, so this is 1 plus or minus 5 divided by 2, and then the solutions here are 1 plus 5 is 6, divided by 2 is 3, and 1 minus 5 is minus 4, so this gives us minus 2. In this case, both of our eigenvalues have a magnitude which is bigger than 1, so therefore this is an unstable fixed point, a source. So here we have the solution.